Number of 1 bits. Want to impress interviewers with a classic bit manipulation trick? Number of 1 bits, or Hamming weight, is a pattern mastery 100 must-know and a favorite for roles at Google, Microsoft, and anywhere you work close to the metal. This deceptively simple problem reveals who understands how numbers are stored and manipulated at the binary level. Get this one right, and you'll be ready for any bitwise brain teaser they throw your way. Let's break it down. Given a 32-bit unsigned integer, your job is to count how many ones are in its binary representation. For example, the input here is a number where only a couple of bits are set, and we need to count all of them to get the answer. Now, let's assess our approaches. You could shift and check every bit, but that's up to 32 steps for every number. Can we do better? Yes. With Brian Cunningham algorithm, we repeatedly flip the least significant 1 bit to 0 using n and n-1. This clever trick only loops as many times as there are 1 bits, lightning fast for sparse numbers. Here's the structure. Start a count at 0, while n is not 0. Set n equals n and n-1 to clear the lowest set bit. Increment count. When n is 0, count holds your answer. Let's try to implement it using solution 1. Time complexity. This loop runs a fixed number of times, 1. We start by defining a class called solution. This simply acts as a container for our function, like putting our tool inside a toolbox. Inside the class, we define a method named Hamming weight. This function takes a number n, and our goal is to count how many ones appear in its binary form, also known as the Hamming weight. We initialize a variable called count, which will track how many 1 bits we discover. We loop exactly 32 times, once for each bit in a 32-bit integer. Even if Python integers can grow larger, we treat the number as a 32-bit input because that's what the problem specifies. Inside the loop, we check the least significant bit, the rightmost bit, using n and 1. If this bit is 1, then we found a set bit. If the bit we just checked was a 1, we increase our tally. Simple. Found a 1. Add it to the count. Next, we right-shift the number by 1 bit. That means we discard the bit we just checked and move the next bit into view, like sliding a window across the binary number. This prepares us for the next iteration of the loop. After checking all 32 bits, we return the final tally, the total number of 1 bits we found. This is the Hamming weight of the number. Solution 1. Case 1. N equals 11. Let's test our function using this input, 11. This number represents the integer whose binary form we want to analyze. We're counting how many 1 bits appear in its 32-bit representation. Here's why the solution works. The number 11 in binary is 1011. As we shift through all 32 bits, bit 0 to 1, bit 1 to 1, bit 2 to 0, bit 3 to 1. That gives us 3 ones total. And that's exactly what our program outputs, 3. The function correctly counts the set bits, so this test passes perfectly. So, our implementation is correct. The algorithm successfully counts the number of 1 bits in the 32-bit representation of any integer, efficient, accurate, and reliable, passing all test cases with ease. This time we're walking through solution 2, Brian Cunningham's clever algorithm. Time complexity. Faster than checking all 32 bits. We begin by defining a class named solution. This is just the container that holds the method we're about to create, like putting your code inside a well-labeled drawer. Inside the class, we define a method called Hamming weight. Its job is simple. Count how many ones appear in the binary form of the number n. This version uses a smart trick to skip over 0 bits entirely. We start by setting a count variable to 0. This is where we'll keep track of how many 1 bits we've found so far, like starting with an empty tally sheet. Now we enter a loop that runs as long as n is not 0. Each loop iteration removes exactly 1 bit from the number. So if the number has m set bits, the loop runs m times. This is the magical line. n1 flips all bits after the lowest 1 bit, including the 1 bit itself. When we init with n, we effectively erase the lowest set bit from the number. Think of it like peeling off the lowest on switch in a row of light switches. 1 peel per iteration. Each time we successfully drop a 1 bit, we increase our count. 1 removed 1 bit equals 1 more added to the tally. Finally, After we've removed every one bit from the number, meaning n has become 0, we return the total count, and that gives us the Hamming weight. Solution 2. Case 2, n equals 128. Now let's try the input, 128. This number represents a pure power of 2, meaning it has exactly one bit set in its binary form. For example, 128 is 10 million in binary. When we apply n, and n, 1, that single one disappears immediately. One drop becomes 0. So our counter increases only once, and the function returns 1, exactly what we expect. Another clean pass. So, our implementation is correct. The algorithm efficiently counts the number of set bits by repeatedly dropping the lowest one bit. Fast, accurate, and reliable across all test cases. Alright, let's wrap this one up. This problem was all about uncovering the hidden ones inside a number's binary form, a perfect mix of logic and bitwise precision. Breakdown recap. We began by understanding that the task is to count how many bits are set to 1 in a 32-bit integer. It's simple in concept. Look at the binary version of the number and figure out how many ones are present. Assess recap. Next, we compared approaches. The straightforward way is to check each bit one by one, but that's not very efficient. Instead, we turned to Brian Cunningham algorithm, which smartly removes one set bit at a time using n, and n1. This drastically reduces the number of steps, especially for numbers with few ones. Structure recap. The logic flow was clean and minimal. Start with a counter, repeatedly clear the lowest set bit, and keep counting until the number becomes 0. When it's done, that count gives the total number of 1 bits. Implement recap. We implemented this on LeetCode, and the solution ran smoothly without any errors. Check recap. After testing the code on multiple inputs, every test case passed, confirming the efficiency and accuracy of the approach. The key takeaway here is the elegance of Brian Cunningham's algorithm, a reminder that understanding bit-level manipulation can turn a brute force task into a lightning-fast solution.